Hello guys, so let's look into another topic in physics called force field, where we also explain Newton's law of universal gravitation and we solve some various questions based on the examination bodies we have been working on. So if you are just coming, please click on the subscribe button and click on the bell beside it to notify you when we drop a new video. And if you are not new here, thanks for coming back again. So let's proceed on the topics for today. We have force field. Anyway, we are all familiar with what force is. Anyway, if you are not, force is defined as the push or pull of an object. Fine. And as we all know, we have a contact force and we have a non-contact force. We have three types of contact force, which are the push, pull, and friction. So then we have the non-contact force. This non-contact force, they act around a field. So that is why the topic is called force field. So when we talk about non-contact force, we are referring to electrical force, gravitational force, and magnetic force. So talking about force field, now we're talking about a space or region where a body experiences the effect of a force by some physical agencies. And those physical agencies are the one I mentioned earlier: gravitational force, electrical force, and magnetic force. So talking about Newton's law of universal gravitation, that means we are going to emphasize more on gravitational field. And we are going to come back on different videos for electrical and magnetic field. So talking about gravitational field, from the definition of force field, we can derive that of gravitational field. Force field can be defined as a space or region where a body experiences the effect of a force by some physical agencies. Now we want to specify for gravitational force, so we can say gravitational field is a space or region where a body experiences the effect of gravitational force. So that is gravitational field. So now let's move straight away to Newton's law of universal gravitation. Though before we move into that, we need to explain some certain things. We know that we are much familiar with planetary motion, and we in the days of Aristotle and some ancient scientists, the idea was that there is a kind of spirit or monster that is pushing the earth around the sun and so on. But with the discovery Isaac Newton has made, it has proven that the gravitational force is responsible for the movement for the revolution of the earth, even the rotation of the earth. So the gravitational force is responsible for that. And we also have Kepler's law that governs the planetary motion, so which we are not going to explain in details as far as light is concerned and JAMB. So let's go straight to gravitational force between two masses, which is the major bedrock of Newton's law of universal gravitation. So when we talk about two masses, suppose we have two masses, m1 and m2, which are of distance r apart. This is their distance apart. There exists a gravitational force between those two masses, which is the same thing as the gravitational force that exists between the moon and the earth. The moon revolves around the earth because there is a particular force that exists between them that tends to drag them together, but due to a certain force that prevents their conniving, so the moon is able to move around the earth's crust. So now, as part of it, this force we are talking about that involves the movement of earth and moon in circular paths is called centripetal force. Don't forget, centripetal force is a force that keeps a body moving in a circular path. Though centripetal force is also a gravitational force, its part is a fraction of gravitational force. So there is a gravitational force between two bodies. But here we want to consider it on the surface of the earth. So now, two masses m1 and m2 have distance r apart from each other. There is a gravitational force between them, just like practically I do tell people that when you stand beside each other, there is a force between the two entities. You know, by the time you are trying to fall on the other person, if there is no force of gravity, definitely you will not be able to fall. I also relate it with the ground side of it because if you can fall on the ground, that means there is a gravitational force between you while standing and the ground. The only time you have no force acting on you is when you are lie down straight, you lie down flat on the floor, on the ground. So you have no net force of gravity acting on you at that moment because you cannot fall again. So there is always a gravitational force existing between two bodies, provided there is a certain distance between them apart. So the Newton law of universal gravitation states that the force of attraction that is between these two particular mass, two bodies, is directly proportional to their product. So meaning that this force, there is a force that is existing between them, force of attraction, F, that is existing between them. So this force of attraction is directly proportional to the product of the two masses, and the force is inversely proportional to the square of the gap between them, which is the distance between them. So we can state it, hence we can state the Newton law of universal gravitation as the force of attraction between two masses is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. So now, joining these together in joint duration, we're going to have F is equals to, I will have a constant. Anyway, let's say directly proportional to m1 dot m2 all over r squared. So here I'm going to have a constant which is g, m1, m2 all over r squared. G is a constant called the universal gravitational constant. Universal gravitational constant. Universal gravitational constant. Then don't forget the value of G is 6.67 times 10 raised to the power minus 11. Though the unit, if you have to get the unit, making G the subject of the formula here, I have F r squared over m1 dot m2. Don't forget the masses of two bodies is measured in kilogram. So we're going to have kilogram squared. Force is measured in Newton. Distance in meter, that's meter squared, all over what? Kg squared. So we can have Newton meter squared per kilogram squared. So this actually is the unit of G, which is called universal gravitational constant. So we can look at varieties of questions that will involve the usage of this formula or the application of this formula. So let's check previous questions that will require the use of this formula before we proceed to the next level. Let's look at a question that says the mass of the planet Earth, is about 6 times 10 raised to the power 24 kg. So let's say mass of the planet NP, which is 6 times 10 raised to the power 24 kg. So this is the mass of the planet Earth. And that of the moon is about 7 times 10 raised to the power 22 kg. So mass of the moon is 7 times 10 raised to the power 22 kg. Is that right? 7 times 10 raised to the power 22 kg. So the distance between the Earth and the moon is 4 times 10 raised to the power 8 meter. The distance r between the Earth and the moon is 4 times 10 raised to the power 8 meter. Good. Using Newton's law of universal gravitation, find the force of attraction between the Earth and the moon. So we are meant to find the force of attraction F between the Earth and the moon. Don't forget G is 6.67 times 10 raised to the power minus 11 Newton meter squared per kg squared. So from there, using the formula we have just derived, using F equals G M P dot N M all over R squared. So I can have F is equals to 6.67 times 10 raised to the power minus 11 times the mass of the planet, which is 6 times 10 raised to the power 24, times the mass of the moon, which is 7 times 10 raised to the power 22, all over r squared. So r is 4 times 10 raised to the power 8, all squared. So from here I can have 6.67, solving in standard form, times 6 times 7, all times 10 raised to the power minus 11, plus 24 plus 22, all over, this will be 4 squared and 16 times 10 raised to the power 8 times 2, which is 16. So applying the calculator, let's see how it goes. 6.67 times 6 times 7. So that gives us 280.14. I have 280.14 times 10 raised to the power n. When I add this, 24 plus 22, so that gives me what? 46. So minus 11 plus 46. So that is going to give you what? 35. So I'm going to have 35. All over 16 times 10 raised to the power 16. So dividing, I'm going to have 280.14 divided by 16. All times 10 raised to the power 35 minus 16. So I'm applying the law of indices here. This division changes to minus here. So then I have 280.14 divided by 16. So that gives me 17.51 times 10 raised to the power 35 minus 16. So that gives me 19. Yeah, 19 Newton. So this is the force of attraction between the two bodies. The force of attraction between the two bodies. So that goes. Let's look at gravitational potential as another subtopic. Then we look at questions to solve like that. Gravitational potential. When we talk about gravitational potential, we are emphasizing on, okay, let me give an explanation. It is said that it is the work done in moving a body from one point to another in a gravitational field. So the work done moving a body from one point to another in a gravitational field. If I am holding these two markers, this one is at this distance, I, and this one is a little bit lower than this, as you can see. Now, this one and highest height have more gravitational potential than this. You know, potential energy has to do with, let's relate it to that. It has to do with energy that you possess. Is a stored energy that you possess and you have not started using. So, if they are to start making use of their gravitational potential, so much work will be done to bring this down, not by the body, but by gravitational force. So this body is performing no work, but gravitational force is responsible for moving it down, so that is why we call it gravitational potential. So it is not a kind of work done by the object itself. So when you are moving this body down towards the ground, and this also, this requires more gravitational potential than this. And anyway, even if in a gravitational field we are meant to move a body from one gravitational point field to another, within the gravitational field, I mean, from one point to another in the gravitational field, the gravitational potential also comes in. There is work done in doing that. If you are to move a body in gravitational field, definitely you are going to work. You are going to work against gravity. Okay, taking this body right from here to this point, at least this is the gravitational field. So moving it against gravity, work will be done anyway. So we define it as the work done in moving a body from one point to another in a gravitational field, and it is denoted by V. So which means gravitational potential. So and at the same time, since we are emphasizing on one body, the gravitational force on one body, the work done is moving a body from one point to another. So we are less concerned about two masses. So the formula is G m over r squared. That's the gap, the distance. You are taking the body over the distance, a particular distance. I'm taking this from this gravitational field, from this point within this gravitational field, I'm taking it from this point to another point. So definitely I'm working. So the work I'm doing on the gravitational potential is going to be calculated using the mass of the body over the distance it's traveled squared. Distance is traveled. But anyway, it is always negative because you are working in the gravitational field is going to be negative. So I think we need to have a negative sign here. Yeah. So from there, we can determine gravitational potential as the question comes. So one more thing we need to look at is escape velocity. Escape velocity. Escape velocity. What do I mean by escape velocity? That doesn't actually mean the speed a thief will take to escape from a policeman, or probably the velocity a car will take to escape from hijackers and so on. No. We all know that gravitational force is deeply submerged into the earth, on the earth crust. I mean, gravitational force on the earth crust is very, very high. So we are into the pool of gravitational force on the earth crust compared to the space. So talking about escape velocity, we are considering a speed or a velocity a body can take to escape the gravitational force on the earth crust, then move out into the space. Let's consider this. If I'm throwing this, no matter how, a point is going to reach. It's going to reach its maximum height, just like a projectile. Then once it's reached its maximum height, because of the influence of gravitational force, it tends to come down. But what speed can I throw this? To the extent that the gravitational force will not be able to act on it until it gets out of the earth's crust and move into the space. So that particular speed that is going to be given to a body for it to escape the gravitational force and move out of the earth crust is referred to as escape velocity. So it is the minimum speed required by a body to escape the gravitational force and move out of the earth. Professional definition. That is it. So now, this principle of escape velocity is used in the propulsion of rockets out of the space. If you notice, a certain amount of fuel is being burned to release the energy for the rocket to move out of the earth crust and right to the space. So this amount of energy that is evolved gives the rocket that velocity that it takes to escape the gravitational force. So now, I have a way of determining the formula for escape velocity. How can I know the velocity I'm going to give to this particular body for it to escape the force of gravity? There is a formula for it, but I generally derive it by merging the potential energy of the body with its kinetic energy at a moment. Like, you know the potential energy of a particular body at the moment, and you know the kinetic energy of that body. Equating the two together and solving out, you can get your escape velocity. Or like in some textbooks, you will see work done equated to work done on the body equated to kinetic energy will give you escape velocity. Anyway, so that's also acceptable. If I would have said that, I can say if we are traveling a distance r, the work done is going to be what? The mass of the body. Traveling the distance r, vertical distance, talking about against gravity. So the work done on the body is mgh. Don't forget, h is vertical height. So I'm making use of r in place of h here because I have a reason. We have been using r over for our distance. So now, mgr. From there, this is also the work done by the body. If I equate this to the kinetic energy of the body at that moment, the same body, the mass will cancel the mass. I'm going to have gr, which is equals to half v squared. So v squared equals to what? 2gr. So v will be what? Square root of 2gr. So this formula is for calculating the escape velocity of the body. Square root of 2 times gravitational acceleration due to gravity times the distance it is meant to travel. So if we are to know that okay, the distance from the surface of the earth outside the space is so distance, then we can make use of this formula 2 times acceleration due to gravity times distance the square root, and to give us the escape velocity of such body. So finally, before we start solving questions, let's look at relationship between this acceleration due to gravity and universal gravitational constant. So don't forget we have F is equals to G M all over R squared. So don't forget when we talk about acceleration due to gravity, we are referring to a single body, acceleration of the single body due to gravity. Look at this. Though work is done on it to work for it to move forward because we are working against gravity, but while coming down, no work is done due to gravity. So and the body accelerates with a certain value which is 9.8 or approximately 10 meters per second squared. So which is called acceleration due to gravity is a constant. So don't forget G is 10 meters per second squared approximately. So now, what will be the relationship between this universal gravitational constant and acceleration due to gravity? Let's see. Don't forget that F, which is force, is equal to mass times acceleration due to gravity. Talking about force on gravitational field. So we can have G m1 m2 over r squared. So since we are considering a single body here, so the mass can definitely cancel 1. So then we have G equals what? Gm over r squared. As we can see, almost the same thing like gravitational potential, but just that no work is done here, so it's not negative. Acceleration due to gravity is just like gravitational potential, but since there is no work done, we are not losing energy. You are not losing any energy, but here you are losing energy because you are working against gravity. So from taking this body from one point to another in the gravitational field, you would lose energy because you are working against gravity. But gravitational force, the influence of gravitational force itself creates this, so it's going to be positive. So that's what we call, that's the relationship between acceleration due to gravity and universal gravitational constant. Thanks for watching. Please subscribe to our YouTube channel. It's free. Thank you.